In the last video, we talked about the basic physics theories of Isaac Newton, mainly the universal law of gravity. In long story short, you can go watch the video if you're interested in that. But long story short, Isaac Newton's theory of gravity says that if you drop an object near the center of the Earth, near the surface of the Earth, sorry, then it will accelerate towards the ground at 9.81 meters per second squared. And I should actually add that if you're confused about why it says meters per second squared, think about meters per second. So meters per second is the velocity. So it's basically saying how fast the velocity changes every second. So that's the consequence of his theory, but it's actually not useful. We don't really care how objects accelerate or how fast they move. We really care about the distance they cover. That makes the most sense when you think about it. So in order to explain the problem, you need to also understand another view that Newton had that obviously makes a lot of sense, and that's basically the view that space is continuous. So space is continuous. Now, I should add that modern physicists, a lot of them, do not believe that space is continuous. But what I would say is that even if you don't believe space is continuous, the difference in steps in space are so small that you might as well assume it is for the sake of understanding situations. So basically, what Newton thought is if we go back to our example above, where you have an object that you drop from a certain height and it's hitting the ground, and let's say at some later time it gets this far, so it's falling down. Uh, this is at t equals 0, and this is closer to the ground. Basically, what Newton said is not only the ball is not falling in discrete steps. Basically, at every point in between the height that it's at now, so if we go like that, basically divide that, the ball is covering all these distances, so at some other point in time. So what we're really taking is we're taking a snapshot. You can think of it as taking a snapshot on your camera and seeing how high the ball is at various seconds. So maybe every 1 second you take a picture to see how high the ball is, and you see it start up here. 1 second later, maybe it's down here. 2 seconds later, maybe it's here, and then maybe 3 or 4 seconds later, it hits the ground. But you don't have to just take the picture every 1 second. Theoretically, you could take a trillion pictures over 4 seconds. So let's say, it takes 4 seconds to hit the ground, and you take 4 trillion pictures. Well, or sorry, you take 1 trillion pictures. That means you're actually taking a picture every, 1 times 10 to the 12, or sorry, yeah, seconds. So, yeah, that's a very small number. That's basically you're taking a little tiny snapshot as you move ever so slightly. So as the ball just falls a tiny bit, so as the ball you take a picture, and then as it falls a tiny bit more, you take a picture, tiny bit more, tiny bit more, tiny bit more, and the idea is you can actually make an infinite curve about how the ball falls. So this is what we're trying to do when we actually graph the distance that the ball, or the height in this case, that the ball falls. So if I try to draw here, let's say for the sake of argument, um, we'll actually say we're actually going to flip this around. So we're actually going to call this the basically distance, and it's going to be equal to or distance equals starting height minus current height. So that sort of makes sense. So like if you think about this, we're not really asking what the height of the ball is in this case. We're really asking how far has it fallen. That's what we're doing here. And let's just say for the sake of argument, the curve looks like this. So it obviously starts at 0 because before we let go of the ball and drop it, it's not falling. It's still at the same starting height that it was. But as it gets, and obviously over here, let's say it hits the ground, what path does it follow in between those steps? Let's just say, for the sake of argument, that it follows a curve that looks like this. Now, you can ask me at every single point in time between 0 and let's call it, TF for final. You can ask me at every single point in time how far that ball has fallen, and I can give you an answer. That's sort of what it means to be continuous. It's not like the ball, it's not like the ball starts here and magically teleports 1 second later down here. No, it's not really teleporting. It's falling continuously. At every point in time, it's getting a little bit closer to down there. Now, it's in that's basically the idea that Newton had in his mind when he was thinking of continuity. So if we take this curve, there are a couple questions that we could ask. One thing we could ask, remember, Newton's law says that the acceleration is a constant. Or actually, let me just write. I don't have it's actually 9.81 meters per second, but the acceleration is constant. That's what his law says. It doesn't say that the distance covered or the velocity covered is constant. It says that the distance is constant. Or sorry, it says the acceleration is constant. So if you imagine that, basically what that means is we need to come up with some way to like go between distance and acceleration. Now, it's not obvious how we do that, especially with continuously varying functions. But we do have some algebraic definitions. So for example, the definition of velocity is equal to the change in distance. That's what this means, change in d. And I'm actually going to start using x because that's how most people use it in any course that you see. Remember x, we'll call this x. So this is x that we're graphing. We're graphing x by t. So x is basically the distance that it's fallen in this particular case. So this is actually the algebraic definition of velocity. And then obviously the algebraic definition of acceleration is this rate of change of velocity, or sorry, the change of velocity divided by the change in time, which in total gives the rate of change of velocity. So if you think of the change of velocity, what you're really thinking of is basically how much distance something covers divided by how long it took it to cover that distance. So for example, if you're in a car and you're going 60 miles per hour, what that means is that in 1 hour you've covered 60 miles. If you're going 30 miles per hour, what that means is in 1 hour, in other words, hold the denominator constant, 1 hour, you've covered 30 miles. Now you don't have to be going at the same speed throughout that journey, but you do have the same average. So for example, we can sort of apply this idea to the distance function. We can basically use a stopwatch to count how long it takes to hit the ground. So let's just say that's TF, and we'll call this TI for T initial, time initial, and time final. And then we obviously have X final, and then X initial right here. So we're good. If we think of it that way, then you can actually find out what the average velocity of the ball that's dropping is over this entire interval is you can basically say how high did you start. So v equals it would be, or sorry, let me write x final minus x initial divided by t final minus t initial. Now you might ask, why are we doing final first? Well, think about it. If we want to have a positive distance, let's say the distance that we cover increases. So in this particular case, the ball falling down is positive. Now let's imagine the ball magically goes up in the air. Well, we would call that a negative displacement. It's actually, displacement is a better word than distance here. Displacement basically means displacement can basically be positive or negative, but distance is actually the absolute value of displacement, which means it's always positive no matter which direction you go. So I'm going to start using the word displacement here. If the ball is falling in the positive direction, then x final is going to be down here. In other words, it's going to be a larger x compared to where when we started. So if you do a larger number minus a smaller number, that'll give you a positive velocity, which is what we want. Whereas, let's say the ball went upwards, and we would say that's in a negative direction, well, then that would give you a negative velocity because you have basically a smaller x final minus or a larger x final. Sorry, you would have a more negative x final subtracted from a more positive x initial, which would basically make your velocity negative. So that's basically the reason why we do it in this specific way. Now, if you think about that, what we can do is we can say, okay, x final minus x initial, that's basically the height in this particular example because we're basically starting the ball up here. It's going to hit the ground. Obviously, the total displacement is the height. It's how much distance it covers right before it hits the ground. And we can actually count the amount of time it takes to do that. So we can, at t initial, we can hit our stopwatch. So let's say that's at 5 seconds, we hit our stopwatch, and then when it hits the ground, as soon as it hits the ground, we click our stopwatch again. And now our stopwatch says 8 seconds. So we would have, in this example, let's just assume the height is 10. So let's say it covered 10 meters divided by 0 meters. We're just calling this height here 0 to make things make more sense. Just for sorry about that. Just for the sake of analyzing it more easily, and let's say we started our clock at 5 seconds, we said, and we stopped it at 8 seconds. If you add this up, you would actually get 10 meters divided by 3 seconds. So this is like 3.3 meters per second. That's basically what that means. That's a speed of, that would be like, with these assumptions, the average speed was 3 meters per second. Now here's the critical insight that Isaac Newton had. Just because basically, how should I explain this? Just because that's the average doesn't mean that just because that's the average does not mean that is what the ball is going at every single point in time. So if you think about, if we actually graph this, if we think of, x, or we think of the final displacement minus the initial displacement as the rise, and we think of, over here, the t final minus t initial as the run, then obviously, if you're familiar with basic algebra, the slope equals rise over run. So we would actually have a slope between these two endpoints. And the slope of this graph right here represents the velocity. So I'm gonna move down to make more space, but I'm just gonna kind of run with this concept. So if we think about our, here we have our graph. And we think of our definition of velocity as x final minus x initial divided by t final minus t initial, which is just, the change in displacement divided by the change in time. That's the algebraic definition of velocity. We can think of that on the graph as the slope from here to here. It's a straight line. But that's really not accurate because, it might tell you what the average velocity is. So this is actually the average velocity. But that was not enough for Newton because Newton wanted to get a lot more accurate. He didn't just want to know what the average velocity is over the whole path. He could do that with basically algebra that had already been created at the time. He wanted to know what the speed was approximately at every single point in time. So in other words, if you give him a time, he can tell you how fast the thing was, or how fast the ball was falling at that time. You might ask, well, what's the idea? How would you explain this? And it's sort of a difficult concept. One thing you need to do is basically create a function for this curve. So I'm just going to say a relatively simple function that x over t equals t squared. So in other words, if you give me a t, you multiply it by 2, or you square that number, and then that would tell you how much distance it's covered at that time. So for example, at 0, we obviously have covered 0 distance because we're still holding the ball in the air. We haven't let it drop yet. Say after 1 second, we're here. Actually, yes, let's say after 1 second, we would be, maybe say somewhere in here. And then after 2 seconds, we'd be up at like x equals, or up at displacement equals 4. So that kind of represents the curve here. So let's just run with this idea. So the first thing you need is a distance or displacement function. Got that. And then here is the critical insight that makes calculus work. That it's basically, calculus is basically algebra plus this one very simple idea. Let delta t shrink very small around whatever speed you want to find. You might not know what I mean by that. I'm going to get into this in a bit more depth here, but let me actually make a little bit more room and redraw. So remember, we're saying that we have our graph here. We're graphing the displacement x over time, and we're saying it follows the curve approximately t squared. X equals t squared. So that means if you give me any time, so time equals 0, we'll start it at 0, and then let's say it goes up to 4. Let's use actual numbers here just to make a better idea. That would be, 16 right here. So this would be 16. At 16, at 2, this would be about 4. At 1, this would be 1. And this actually looks a lot better than the graph I drew before. This would be 9. So in other words, when t equals 0, so when we just start, we haven't covered any distance. When we let the ball drop for 1 second, it's fallen a total of 1 meter. When we let the ball drop for 2 full seconds and see how far it's fallen a total of 4 meters. 3 full seconds, 9 meters, 4 full seconds, 16 meters. That's this equation. And we can find any number in between too. So you can literally find, 1.0157 seconds later, how far has it fallen? And if we just assume that the equation is accurate, which is an assumption we're making just to understand right now, then you would actually be able to tell exactly how much distance it's covered. Now the idea, remember, with our average velocity is that we're finding the velocity on the whole interval here, which is this slope. So Newton's idea was, okay, let's say we wanted to find the speed at t equals 2. What would we do? Well, we know what the speed is at the entire interval. So here's an idea. Why don't we just, and we know how to, over a certain interval in algebra, we know how to calculate the distance. It's literally just rise over run. It's the final minus the initial. So why don't we just use that idea to make a really small interval around the thing that we're interested in? So instead of trying to calculate from here to here over the whole interval from when it takes, when you let go of the ball until it hits the ground, why don't you just use that algebraic equation over a really tiny interval around what you're interested in? And obviously, as you let this interval shrink, it's going to get a lot more accurate. So the equation that implies is actually velocity as a function of time. Remember, it's going to be a function of time. Is going to be equal to, or it's going to, let's say it's not going to be exactly equal to. It's going to be approximately equal to. Let's make it really small. Let's use a delta t of 0.01. How about that? So that's a really small time interval. So that's like at t equals 2, you would measure how far it's fallen, and then literally 0.01 seconds later, 10 milliseconds, a very small amount of time, you would measure it again. And it would be slightly higher, and then you basically plug into that equation. We would do x of 2.01 minus x of 2. Whoops. and then we divide that by 0.01. Remember, this is delta x, how much has the displacement changed, divided by t. This is the same algebraic equation we used above. So like here we have, the final displacement minus the initial displacement divided by delta t. You could represent t either way here, but we're just going to use delta t because it's easier to derive an equation based off of that. The only difference here is that we've just shrunk the interval. So instead of t of f being say 4 and t of I being 0, we're just doing a very, very tiny interval around t equals 2. So if you actually calculate this, what would this be if you actually calculated it? It would essentially be 2.01 squared, because remember, x of t is equal to t squared here. So take whatever number you're plugging into the x equation and square that. Or sorry, I already squared it, it looks like. So yeah, take that number squared minus x of 2, which would be 2 squared, and then divide that by 0.01. If we actually run with that, actually let me use my calculator real quick. I have an idea of what it's going to be. I just want to make sure I get it exactly right. So 2.01, you can do this on your calculator to verify. That's going to be 4.0401 minus 2 squared, which is obviously 4, divided by 0.01. All right, we know how to solve this, so we're looking at basically 0.0401 divided by 0.01. So let's do that. 0.01, divide my answer on my calculator. Let me see here, 0401 divided by 0.01. We get what we get when you type that into your calculator is, drum roll, approximately 4.01. So that's interesting. So when t equals 2, then the velocity is approximately 4.01. Now that's a bad circle. That's actually kind of interesting because it almost looks like it's exactly double. So it's not exactly double, but remember, this is only an approximation. So you can see with this idea, you can actually, assuming you have a function, a distance function, x of t, you can actually find the velocity with a very high degree of accuracy at each point in time t by following this equation, this algebra equation that's essentially the definition of velocity. And you can use the same thing if you have the velocity equation, you know that at each point in time, then you can actually use the same thing to find the acceleration, which is what Newton wanted. Because remember, he knew that the acceleration, or he believed at least based on his theory, that the acceleration was constant at the surface of the Earth when you drop an object. And he wanted to show that he basically wanted to determine what the velocity function is based on that concept and what the distance function is. And then also for any arbitrary accelerations. A constant acceleration is really just the easiest case. So this is the basic logic that he used, and now we're going to ask the question, how can we tidy this up? Because that's great that we found, what we basically just did was we basically just found what the velocity is at t equals 2. We found the speed, or the velocity, at time equals 2. But there's an infinite number of times. Remember, Newton viewed time as being continuous. You could say we have time 0, time 10, or we can cut that in half, time 5, cut that in half, time 2.5, that in half, 1.25. You can do 0.00000001. That's a valid time. You can choose any number really to represent time. So what Newton really wanted to do was he wanted to generalize this idea. He wanted to not only find what the velocity was at a specific time, in this case 2, what he really wanted to do is he wanted to find an equation for everything. And now I'm going to show you that equation now. And in case you haven't noticed, what we're actually getting into is the derivative. So this is basically half of calculus that we're getting into now. So what Newton found is that the velocity is equal to And this is where we add calculus. Calculus, it's just algebra with limits. That's all calculus is. But we're going to add this new notation here, limit of delta t, limit as delta t approaches 0 times x. Remember, x is our displacement function. X of t plus delta t minus x of t all over delta t. There we go. So this is the derivative right here. So I may actually get rid of this here to make room for the derivative. So this is actually sort of a big deal. This is the equation for derivative, which is basically half of calculus. The other half is integral calculus, which we can get into later. Now, you might not really know what to do with this here, and this might not make any sense to you, but let me just remind you, let's just use the specific numbers that we used before. So remember, we use this idea of just shrinking the interval along here. So remember, just to refresh our memory, what are we talking about? We're talking about having an equation like this being t equals 2, and what we're saying is, instead of approximating the velocity from t equals 2 to t equals 4 over the entire interval, why don't you just shrink it really small from here to here and then take that slope? Doesn't that make a lot more sense? Because the slope changes a lot from 2 to 4, but it really does not change a whole lot from 2 to 2.01. So taking a much smaller sample gets you a lot closer to what the speed actually is. And by the way, the speed geometrically, you can think of it as the tangent to this graph. It's basically the straight line that touches the curve at one point, at the point you're interested in. So that's sort of the geometric interpretation of the derivative that you'll probably see a lot in your classes. But anyway, if we just use the basic numbers, we would use 2. That's the number we're interested in, plus 0.01 minus x of 2 divided by 0.01. So if I compare this equation here with this equation up here, you can see that they're the exact same. So 2.01 is just 2, the number that we're interested in, plus some small delta t, 0.01. And then it's all divided over 0.01. So that's here. The only difference in calculus is that we're not actually calculating it with algebra. What we're doing is we're using limits. So we're not stopping at a small limit either. We're actually just seeing what it approaches as t goes to 0. Now, you can't actually just directly plug this into 0 because, obviously if you plugged in 0 for delta t, so let's say we tried to solve this equation. So x of 2 plus 0 minus x of 0 divided by 0, or sorry, this should be x of 2. What are we going to get? That's 0 over 0. We can't calculate that. So that's the whole reason why we need this new term limit. We can't just evaluate this for some delta t of 0. We have to basically plug in a bunch of really small delta t's to see what it is. So one way you can think about that, just one way to kind of ease into our equation for the derivative, and basically how you can use that. You can think of it as essentially making a table where you use, let's say, or I should say delta t. Actually, let me redraw this a little bit. Let's say we have some table where we have delta t, and we basically have v of or let's say we're evaluating it at a specific value. So we have this. So like we'll start off with an interval of 2, then 1, then 0.5, 0.1, 0.0001, 0.000000001. You can always make this smaller as long as it's not 0. And basically the idea of limits is that as you get closer here, obviously it's going to get more and more exact to the answer, but it'll never be the exact answer. So that's sort of what this limit means. It means We're never going to plug in 0 because that gives us nonsense. 0 over 0. You can't divide. You can't do that. You can't divide anything by 0. If you have 0 over 0, that's an undefined equation. But what you can do is do 0.0000000000001 and then see what that answer is. So what you would do in this particular case, if we're assuming that x squared, assuming that the equation that we're dealing with for x is x equals t squared, then what you'll find is that if you do it for 2, and I'm not going to do the exact values here, but as you get closer and closer down there, what you'll realize is that the answer you get is basically like 4.000000001. So if you use this really small number here, you'll get something that looks like this. In other words, it's never going to exactly equal 4, but no matter, as you make delta t smaller and smaller while still being larger than 0, it's going to get arbitrarily close to 4. And that's sort of what we mean by a limit. That's what this whole LIM thing here means. It basically means if we kept calculating this over and over with smaller and smaller delta t's that are always more than 0, what would happen? And that's sort of the idea of a derivative. This is the kind of official logical equation for a derivative. And basically, if we find some way to actually calculate with these limits, then we can actually create a velocity for each point in time, which is handy because if you think about it, we started this off with an equation for distance over every point in time. So at every point in time, you give me a point in time, I'll give you a distance, and then if we can actually calculate, we can actually basically create a function for velocity. So like, let's say for example, we have, I'm gonna say this is t equals, yeah, I'll just say that's t actually. So that's t, and then let me separate these. So we do that, and here's another t. If we actually have an equation, let's say this one up here, this one up here is distance, and this one down here is velocity. But let's just say we have this equation here, which shows the distance over time. What we basically are trying to do is come up with a way to make some velocity equation that at every point in time we can know how much distance it's covered and what its speed is. And the reason we want to do that is because if we can do that once, we can do that infinitely many times. If we can create a full output function from the input function based on this idea, then we can keep going. And you know what comes next after velocity, right? It's acceleration. Why do we care about acceleration? Well, because Newton's laws say that the acceleration is 9.81 meters per second. So our ultimate goal here is to use Newton's equations, which imply that the acceleration due to gravity is 9.81 meters per second, to determine what the distance is of the object at each point in time. Basically, we want to be able to predict how objects move. That's sort of the whole point of mechanics. Mechanics is basically a subset of physics. Newton basically invented Newtonian mechanics with these ideas. And the whole point of mechanics is to be able to tell where objects are going, basically predict where objects are going to be. And we have a very good framework to do that with forces and accelerations, but we still need a new language to basically convert between acceleration and velocity and distance for continuous functions, which more accurately represent objects in the real world. So I'm going to leave that here, and in the next video we're going to basically take apart this velocity equation and kind of look at it in more depth and try to see if we can come up with anything to actually make it useful and come up with some procedure for calculating limits.